So what I'm going to do, I'm going to share my screen now. Can you see my screen?
Yes.
Yeah. Okay, that's good. So I already put some materials in lecture 8. It consists of the presentation file for today. I also have posted 2 links to the lecture given in YouTube, and also some example of using Kalman filter for cruise control system and also sensor fusion. So I hope you already watched the series of lecture in YouTube. The first lecture, this one, this is a bit general. Just want to give you some idea about what is Kalman filter and then how it's work. But if you are interested further with Kalman filter, you can find in the second link, this one. So you can click it, and then this guy is a professor, I think. One lecture about Kalman filter from the beginning until how to implement it. Both videos are really good. I think the first one, yeah, this is a bit general, but I hope you can get some idea on what is Kalman filter, and then what is the use of Kalman filter, which we will discuss also today. But this video, it's more like into technical stuff, going into the equation, the meaning of Kalman gain, for example. So it has a lot of useful information from these videos. What we are going to learn today, it's about Kalman filter, but since the idea and also the derivation has been presented in this video, so I won't go into the this stuff again. But you can just watch the video. So what I'm going to do now is just to give you some idea on how to implement the Kalman filter, which is very useful, and you can implement this method either in many software, so MATLAB, Python, in C++, and then Kalman filter itself is very popular. So maybe I need to give you some introduction about the history of Kalman filter. So the Kalman filter was proposed by Rudolf Kalman. I think he's from Hungary, and then he got his PhD from Swiss Federal Institute of Technology, or ETH Zurich, and then he became a professor in the United States. So during the Apollo program in 1960, one of the problems is that when you send the satellite, not satellite, but the rocket, and then you want to know what is the position and also the velocity of this Apollo. I think the first one, maybe Apollo 11, I don't remember, but the problem is that how to estimate the position and also the velocity given some measurement with noise. So they want to calculate the exact position and velocity, but then the sensor quite noisy. And then Rudolf Kalman, he come up with this idea. He derived a set of procedure, which is now known as Kalman filter. And then it's quite elegant, and it's working really well. even though if you think about the 1960s, the resources for doing online computation is really, really limited. But this is what happened. This is one of the advantage of using Kalman filter, because usually when you want to estimate the state, you need a lot of data from previous previous time step. But in Kalman filter, basically what you did is that you only need few data, and then you're able to estimate the state and the velocity accurately. So it's quite effective method. And if you go into the derivation, you can also find that Kalman filter is the optimal estimator for linear system. So if you have linear system and you apply the Kalman filter, then the error will be the minimum error compared to another method. So the best linear estimator is Kalman filter. But then we know that the real world is not linear. We have a lot of non-linearities. In fact, I think all of the system that we can describe using mathematical equation are non-linear. So what we can do with Kalman filter is that we can linearize the system, and then we can still apply Kalman filter. This kind of technique known as extended Kalman filter. So extended Kalman filter is nonlinear version of Kalman filter for nonlinear system. And then I think in 1999 or 2000, early of 2000, there is also some guys who do some research about nonlinear Kalman filter. And their idea is that instead of linearizing the nonlinear system, they want to estimate the probability density function of the system itself. And the method is called unscanted Kalman filter. So unscanted Kalman filter is a variant of Kalman filter. And then all of this Kalman filter based method relies on some assumption. And the biggest assumption is that your noise should be Gaussian. It should be white noise. And then and this error has zero mean, and you also need to know the covariance of this error. So that is the limitation. You need to have an assumption that your noise are Gaussian. But we know that some system, the error, some sensors, for example, the error are not Gaussian. But many or most sensors that generate data has a noise that Gaussian. So Kalman filter is quite effective for many systems. But if the noise are not Gaussian, then we can use what we call as a particle filter. Basically, particle filter is another name for particle filter is sequential Monte Carlo. So basically, you also generate some data, and then you estimate the probability density function of this noise, and then you do this iteration, and then you can come up with some good estimate without having an assumption that this noise are Gaussian. Okay, so that is only some overview about different technique when we want to estimate the state, given that your sensor or maybe even your model has some degree of uncertainty. So you are in the drones in drones program. Let's talk about the type of noise. You know, accelerometer. You have GPS. What do you think about the noise of GPS or accelerometer? Oh yeah, half of robotic and drones. Could you tell me what is the nature of the noise from accelerometer or gyro or maybe GPS? Anyone? What about accelerometer?
For the accelerometer, I would think it was
Have you
oscillation.
been working with accelerometer before? Come on. It's a oscillation. What do you mean? Soren, you can speak maybe.
For the accelerometers, I would say it's oscillation in the measurement, because if the drone is flying, then it would be vibrating, I would guess.
Soren, hello?
Hello? Can you hear me?
I think maybe
I can hear you, Soren.
You're a speaker.
Mikkel says he can hear me. Or what?
Oh, okay. Hello?
Hello?
Okay, now I can hear you.
Okay. I would say it's oscillation, because when the drone is flying, it would be vibrating due to the wind and stuff. Then I guess the accelerometer would like oscillate.
Yeah, it would be oscillate, but the oscillation actually affect the measurement, the mean of the measurement, not only the noise. But if you think about, let's say that we put the drones on the top of the table, it's stable, and then you run your you calculate the acceleration from your accelerometer. What you can see from this kind of data, it's a bit like very noisy. It's up and down with very small frequency, right? So
then maybe it's the power line, 50 hertz.
That's the what?
The power line, the 50 hertz power in the houses and outside.
Yeah. Sorry. What do you mean about this power line? So let's see if I can find an example here. Oh, okay. Yeah. So this is a type of noise from accelerometer. I mean, you can also get it from your own accelerometer if you have. It looks like this. So or maybe, yeah, like this also. But you can see here that it has almost the same amplitude, small frequency. There is no like there is no pattern like Gauss distribution, like a bell. So this is flat. So actually, this is called. This is almost similar with white noise, and also the distribution is quite. Quite. You can see here that this is the mean, the average, the middle, and then sometimes you have a point that goes beyond, and not beyond, but far away from the mean. So looks like a Gaussian, and therefore you can assume that for accelerometer it's quite safe to say that it's Gaussian distribution white noise. But the GPS, for example, it's not Gaussian. So if you look into the GPS data, it is like jump from one point to another. Sometimes, yeah, it's random, but
it's far away from Gaussian, and it's not white. So actually, when you have or when you want to treat the signal from GPS, you are not supposed to use Kalman filter, because Kalman filter has this assumption that it should be Gaussian. But anyway, some people just use Kalman filter to merge, for example, or to fuse the GPS data and also the accelerometer in order to get a good estimate about the position. And then it's work fine, but we can say that it's not optimal estimator, but you can still use it. Okay, so even though we violate the assumption that the GPS is not Gaussian, but you can still use Kalman filter to fuse your data. Okay, and then we have I have an example to show you how to estimate the position using sensor data from accelerometer and GPS. Yeah. Do you have any question? This is only like introduction to Kalman filter. So last week we learned about the open loop optimization problem, which is one-step MPC. This is called open loop because we didn't feedback the calculation of U into the system. So last week we only solved one block, this one, at time t, but we didn't put the signal, the control signal, back into the system. This is open loop. And then last week I also mentioned that in order to solve this optimization, you need to know about the x0. This is the position at current time, at the present. So this you get it from sensor. This green dot. The problem is that when you have the signal from your sensor, the signal contain noise. So maybe when this your sensors give you this value, let's say this is 5.5, that is maybe not the actual position. Maybe the true one is 5.3, for example, because you have noise in your sensor. So we can use Kalman filter in order to estimate the correct position, given that this your sensor has some type of noise. But if you want to use Kalman filter, then you need to know that you assume your sensor error is Gaussian once more, with zero mean, so the mean is 0. And you also need to know the variance. How do you know the covariance of your error? Some manufacturer actually written the accuracy of their sensors, including the variance error. So you can get this information from the manufacturer of the sensors. But if you don't have this knowledge, then you can estimate by doing some small experiments, like running this, measuring something with your sensor, and then you observe and trying to get the standard deviation, and then basically the covariance is just like square of your not square, but your standard deviation to the power of 2. That is square. So basically, you just you can get it from your measurement itself. So, do you have any question? No.
Just for clarification, I guess.
Yeah.
So whatever we're measuring might have noise, regardless of the actual data, and that noise has to be Gaussian and white, right? With zero mean error,
Yeah,
and a particular covariance.
Yeah, you need to know the distribution. If this is Gaussian, then you can use Kalman filter. If not, I would recommend you to use another filter like particle filter, for example. So you need to determine if the system has Gaussian noise, the error has Gaussian noise or not. And once you determine that it is Gaussian, you need to know, or you need to assume that the mean of the error is 0, and the covariance, you know the covariance. So that's it. Then you can just run your Kalman filter.
Okay, thanks.
Yeah. Okay, this is the basic idea of Kalman filter. So let's say that you are driving your car, and then inside your car also you use some model to describe the dynamic of this car, and then when you derive the mathematical model of about the dynamic of this car, maybe your mathematical model has some degree of uncertainty, meaning that this one x hat, this is from the your equation. So you're trying to estimate this state using your mathematical equation, and it ended up with that you get this this estimate. Let's say this is 10 meters. Okay, so from here, from the beginning until here is 10 meters. And then since you, let's say, use a lot of assumption in your models, so your model has some degree of inaccuracy, and then this inaccuracy could be translated into an error. Let's say that I know that this is the expected mean or expected position from my model, but then I also know that my model has some degree of uncertainty, meaning that maybe the actual one will be here, or maybe over there, or maybe over here. So your model has some degree of inaccuracy. And then you also have some GPS. This is the brown one. So this is a measurement from your GPS. And then your GPS tell you that maybe this GPS or maybe this IMU, let's say IMU, because IMU has quite Gaussian noise compared to GPS. So let's say this the brown one, this is from IMU. And then from your IMU, the reading is that, let's say this is 13 meters, okay? So from your model, you get 10 meters, but from your IMU, you get 13 meters. And you know also that your IMU has some degree of uncertainty. So meaning that the actual position could be could be here, or could be there also. But if you if you're familiar with this distribution, what is the meaning of this distribution? Could you tell me about what is the difference between here and there, for example? Anyone?
I think it's x hat k minus that point, so that we get the area between these two.
Yeah, what I mean is that if you look into the curve, this is like a bell.
Yeah.
So it has a peak, and it has two tails, right?
Mm.
So what is the interpretation of at the peak and at the tail? It's correspond to what? Yes, exactly, Soren. So the mean, likelihood, or probability, sometimes, yeah, actually that's true. Sometimes there is I mean, some literature interchange this this term about probability and likelihood, but let's use the terms probability because basically this curve is called probability density function. So the probability at the peak is much higher than at the tail. So, for example, maybe the probability here, this almost 1. This is actually not 1. It will be 1 if you integrate all of this value. So maybe the probability here is half, but it's the highest, while probability at the tail is only 0.1, for example. And then if you learn about the probability theory, maybe you know also that the covariance is somewhere over here. So somewhere over here is it's called covariance, really related with standard deviation. And basically the area between means minus covariance and means plus covariance has what we call as confidence of interval, I think around 63%. If you want to have 95% accuracy, meaning that you have 95% of probability, I think the location is between the mean and 1.96, if I'm not mistaken. Have you any basis? Have you learned about statistic or?
Yeah, we have.
Okay, that's good. So you're probably familiar with this kind. And then what we mean with zero mean is that, so this is the zero. So we assume this is zero. It's the same with this one. Is zero means. It's zero means because this is your reference. So this is your zero means. And then the variance is to the left and to the right. So this is the variance. Okay. So the meaning that now we have two information. The first information is from your model with this probability density function, and the second information is from your sensor with this PDF, probability density function. And then the idea of Kalman filter is basically you want to estimate the or you want to combine those information from your model and from your sensors. How to do that is basically by just multiplying the PDF or probability density function. If you remember about this PDF Gaussian or normal distribution, I think it's equal to 1 divided by square root of 2 times pi times covariance, and then times exponents. Yeah, I don't really remember, but it's an exponential function. If you multiply to exponential function, it will be also exponential function. So this is the multiplication of the error from your model and the error from your sensors. So now you have a better estimate of your the position of your car, which is this one. So it's really close or with the actual position. So this is the idea of Kalman filter, basically to trying to merge different source of information. Either you are believe in your model and you are believe in your sensors, and then you try to combine both information in order to get a really good estimate. Okay. So let's talk about the system itself. This is a formal form of discrete time system. So basically you have the state xk equal to some, this is transition matrix times the previous state, and you could also have control input, and then this is a noise that enter your system, and this is measurement equation. You also have noise Vk, and then in this problem, when you want to use Kalman filter, you need to have an assumption that this Wk and Vk is Gaussian, this is normal distribution with known variance. This is Qk, this is the variance for W, and Rk, that is variance from for Vk, for sensor noise. And then what we have in here is that we say that the noise between the system from the model and the sensor our measurement are independent, meaning that the expected value of the multiplication of the sensor is equal to 0. So that is also another assumption in Kalman filter, that is the noise should be independent. So yeah, that's it. Basically, this is the general formulation. And then if you remember last week, we were talking about cruise control system. So basically, this that kind of system could be written into this form by using discretization, either using Euler method or Runge-Kutta. So basically, you can ended up with this kind of system. So how about the procedure of this Kalman filter? So first we start with describing your system using some mathematical tools in order to get this model. Once you get the model, the second one is you need to do some initialization. Okay, this initialization. First, you need to guess. You need to guess the initial state. Of course, if you have your sensor, then your initial state could be obtained from the sensors. And then you also need to define what we called as error covariance matrix, this P. It's called error covariance matrix. So what is error covariance matrix? Is the error covariance that propagates when you run your algorithm. Because when you run your algorithms, there is some the error also propagates, right? So this is the terms that describe this error propagation. How to choose this initial? This is the initial matrix covariance error. This really depends on how confident are you with your initial state. If you are really sure that your initial state that you're guessing it's quite close to the actual one, then you can simply set this as 0. Okay. That is the rule of thumb. So let's set this as 0. But if you are really not sure about your initial guess, maybe it's like 40% accuracy, it's really low. So you can put a large number, let's say 1,000 or 100. It's depend on the magnitude of your state, basically. But if you are not sure, then you just put a big number. Okay, that's how to choose this one for initialization. And then the third one is the most important part, is that the Kalman filter, basically it's recursive. So the current estimate are obtained from the from previous estimate. So you do it recursively. And then what is the important things in this equation is quite a lot of equation. If you go into the derivation, it's I think it takes days in order to digest what's going on in this derivation. But what is important here, the result, is that this K, it's called Kalman gain. So what this Kalman gain do is that this Kalman gain will we're trying to minimize here. This is we have a term like priori and posteriori. Priori is that you estimate your state without having knowledge of your data. So this is only from model. Okay, so xk mean xk mean minus. This is only relying on your data. So this is for prediction, and this is called a priori state. But once you assimilate or you integrate the data itself, this in y, this is the factor, data factor, then it's become posteriori. So quite often, if you study about Kalman filter, you often encounter with this kind of terms, priori and posteriori. So the difference is that in priori, you haven't incorporate your data, but in posteriori, you already incorporate your sensors input. So like this one also is exactly. So k is actually the value that scales. That's true. That's true actually. Your measurement and your data. So k will try to minimize this quantity between your data, this data input, and your model, this guy. Okay. The priori, it's obtained from only from model. If you can see here, this is the system description. You don't have any measurement, but once you include this measurement, so this is equal to this one. So this, and then you add this output injection. This is called output injection, basically. So basically, the estimate is equal to your model, which is this one, the priori state, plus this output injection or correction term. So this is called output injection or correction term. And then what you need to do here is that basically you need to determine what is k. Okay. Once you get this k, the value of k, then this value of k will minimize the difference between your input data and your model. And then how to get this k is based on this a bunch of this procedure. You can look into the derivation, and you can also prove that this k optimally estimate this xk. So this is the best one, the best k that you can find if you follow this procedure. This case, this Kalman gain. Okay. Do you have any question up until now? Was it clear about the algorithm?
About the Kalman gain?
Yeah.
It is the one that minimizes the difference between a priori and a posteriori, is it?
No, not between priori and posteriori, but minimize the distance between your data, input data from your system. So let's say that you want to estimate the position. So you want to estimate the position, let's say, and then yk, this is the position from your GPS or IMU. Okay. While this one, this is from your model. It's this one, this guy. Okay. So that is the only difference. Any other question? And then this is some example of where this Kalman filter is used. The first one is sensor fusion. Let's say you have GPS and accelerometer data. And then what you want to do is you want to fuse this GPS data. You get this. You have a GPS receiver with accelerometer data, and then let's assume that this accelerometer data, you get the accelerometer acceleration from for 3 axes. So you have acceleration in x direction, in y direction, in z direction. And then you want to fuse between those data. Do you have any experience on how to use Kalman filter and sensor fusion? Any of you? No? So I hope this this is your first time.
We have studied them, but we haven't tried implementing them.
Okay, yeah. Actually, I already made one example in MATLAB, and I also put this in eLearn. eLearn. So if you open your MATLAB, okay. So let's say that let's assume that you are biking. So you're biking, and then when you are biking, you also bring with you some accelerometer for some reason, and you also GPS, and then you want to estimate your position. Just to simplify, let's think about one dimension. So you are biking or maybe driving, I don't know, or running or jogging in one direction, X direction. You know the information from your accelerometers about your acceleration, and you know your information about your position from GPS. But as you know that GPS is not quite accurate. So what you want to do is you want to fuse both data in order to get a good estimate. The nice thing about GPS is that it will give you an absolute position because it's calculated from the satellite. So it will give you an absolute position. But the frequency is quite low, and then the accuracy, it's I think for GPS is maybe 1 meters. On the other hand, we have an accelerometer. It has higher frequency, but the problem with the accelerometer is that it has bias. So what we want to do is that let's combine those information in order to get a good estimate. So how to do that? First, we think about a model. Okay. And you know that when we are, let's say you are in position, if you want to know your position, PT, let's say this position, your position will be equal to P0. So the current position plus the velocity times t plus acceleration, or not acceleration, but half times acceleration times v square. So if you want to know, or if you are running or jogging with the velocity, not velocity, but known acceleration a, then you can try to estimate your position from the initial position. I think this is quite straightforward formula. Sorry, this is not v but t. Is that correct? So pt equal to v0 plus v times t times plus half of acceleration times t square. And then you could also how about v pt? This is actually Vt. So Vt itself is equal to V0 plus acceleration times t. Okay, so you have two equations. So you have two variables, the position and velocity. And then if you remember that we can write this equation into a vector and matrix operation. Let's say that Pn3 is a vector of this x. So let's say that x is a vector, consists of P, the position, and V, the velocity. So you can write the state space like this, Vt. Maybe just use this kind of symbol, Vt plus 1 equal to xt, sorry, plus some matrix A, let's say, times xt plus b times ut. Do you think you can change this system into this kind of state space form? What is matrix A? What do you think? What is matrix A? If you look into this one, any idea what is matrix A? I would say that A is a matrix of 1, and then delta t. So the delta t is or dt, the time step, and then for the second row, it will be 0 and 1. Can you see how I get this matrix? Anyone? Basically, I look into this kind of form. This is Pt and P0, but then if we think about the propagation between t equal to 1, t equal to 2, t equal to 3. So, for example, the x at time t equal to 3, so x4 equal to a times x3 times plus b times u3. So this is recursive. So if this is a bit make too confusing, then let's change into this one, just to make it. You can also write it like this, delta t. Yeah. How about this one? You think this is clear? So the next position are determined by the previous position times the velocity and acceleration term. So you want to change this guy into state space form in discrete time, and then you, what is A? A is basically this matrix because you have Pt and the velocity. Do you have any question? Is it clear?
I'm not sure about how you got A. Could you explain that again?
Yeah. How
Sorry.
do we get? It's fine. So how do we get A? So you see that this x is a factor of p, the position and velocity. So this is factor of position and velocity at t plus 1. So this is at t plus 1. While this x, the same one, this is a factor of velocity and position and velocity, but the time is that at t. So this is t plus 1, this is t. Meaning that if you look into this guy, okay, if you look into this guy, the first row would be 1 times p at t, and the second one is you have dt times vt. Can you see that?
Yes, it's fine, but I mean on the second line, I mean second row.
Oh, this one, 0 and 1?
We don't have any p, so we give 0, right?
Yeah, that's true. We don't have p. That's why
but for v, we have, okay, for vt we have 1.
Yeah,
okay.
we have 1. Yeah.
Okay. I was thinking it should be a, but it's not a. We are taking for vt. Okay.
Yeah, this is the trick actually. So what is a? What is b? Sorry, b. You have matrix b. Then matrix b would be, the first one is half of dt square. And the second one would be basically dt. Okay, so in this case, actually, what I'm considering is that I consider u. I'm consider a, the acceleration. This acceleration, I consider this acceleration as the control input. Okay, so this acceleration is the control input. Okay. Wait.
So for B, we are having changes in A.
Yeah. So A is this acceleration, this u. So meaning that this equation of motion could be written in this kind of state space. Okay. Where u, basically this is the acceleration. Now this u is acceleration. Okay. Now you have your state space. And then how about the measurement? Let's say that you can measure.
August?
Yes?
If you pull down in the right corner of the white page, you can make it big. Yeah, then you can show it all if you pull it down.
Yeah, thanks. Yeah, you're right. Yeah, that's right. And then, so you have your state equation in state space. How about measurement? Let's say that you are only able to measure the position. So if you are only able to measure the position, then your measurement matrix, let's say like this, will be equal to matrix C times xt. Now what is matrix C? If I only able to estimate the position, then matrix C will be equal to 1 and 0. Okay, because then 1 and 0, and then you multiply with v and v, it's equal to, basically this equal to position. No, sorry, this guy, it's equal to position. Right, so you able to measure position. And how do I get this position? That is from GPS signal. Okay, so if you can see this kind of system, you have u, which is your acceleration. So you know the acceleration, and then you know also the position from this from your GPS. So your GPS signal will goes into the measurement matrix, while your acceleration data will goes into your state space. Okay. So how to implement this in let's say in MATLAB?
Agus.
Yeah.
Just for understanding, could you go back into If you want to find velocity, then C should be dt and 1.
If you want what?
If you want to find velocity, say.
Oh, yeah. This is actually output factor.
Yes.
Or measurement factor, meaning that if you only have measurement in your in your position, then it will be like this. But if you also have measurement in your velocity, it will looks like this. Identity matrix. Okay. And why is that? Because then if you multiply C and X, then it will become a factor. Like that. Oh. So now Y will become a factor. But so it's really depend on what kind of sensors do you have. If you only have one sensor to measure one variable, which is the position, then this matrix C will be like only 1 and 0. But if you have if you're able to measure all of the state, it will become equal to identity matrix like this. So in this example, let's say that I have an acceleration data from accelerometer, and then I define the time step, and then I also need to define the system itself. So you can see here that this F actually equal to matrix A. It's the same. So basically, this matrix A. Sorry, I often use the different symbol, but this F is similar with the description here. So this F. And then you also have matrix G, that is for inputs, this one. And also you have H, that is for measurement matrix, this one. Or in our previous derivation, that is C. So C is equal to H. So now you have the system description, which is F, G, and H. And then here, I assume that we know the covariance matrix. And the covariance matrix is given by Q and R, like this. Q. Can we run this? Actually, I missed something in here. This Q should be 2 times 2. Oh, okay. I need to clear the... Okay, now it's fine. Oh, what happened? Okay, can you run this program? I checked it like last yesterday. It's working fine. Yeah, that one actually. But what happened here? Maybe I made some mistake. But, let me download. Maybe I changed a little bit. So let me download this. Oh, what happened? Oh, sorry, this one, the correct one. Okay, sorry.
I am getting an error
Yeah.
which saying that undefined function or variable sen fusion.
Oh, yeah. Wait, this is really strange. What happened? Oh, now it's working. Okay. Okay, that's strange. Sorry. So now we have this. We have error coverage. Sorry, actually, I need to multiply this with I because the coverage matrix. I mean, we have two states, meaning that this Q should also a factor of diagonal matrix with the size of 2 times 2. So the Q, this depends on how many variables do you have. If you have 3 variables, then this Q should be 3 times 3 matrix. This should be diagonal. And then R, this is scalar because we only have one measurement, which is the position. If you have 2 measurements, then you also need to multiply this with identity matrix of the size of 2. Okay, and then here you define your initial data. Actually, you can also make this 0. That's fine because we are quite sure that your estimate is equal to your I mean, you are confident that your estimate is close to the actual value. Okay. So this is the procedure of using Kalman filter. So basically, we input, our input is the acceleration from the accelerometer, and then I put this into this one, so it will goes into that one. Okay, and then here what I did in here is that this is a bunch of Kalman filter procedure, which is based on consists of 2 states: the prediction and this update. Okay, so I assume that I have a measurement from GPS and then I put it here. So this is sorry, this one. This is from GPS. Let's say then you have a measurement from GPS, but in this case I generate this from the model, and this signal has also noise, and it's given by random variable like that. Okay, so here what happened in here is that we calculate the Kalman gain in order to minimize the difference between your signal from GPS and your estimate from your Kalman filter here. And then you can see here that the estimate is quite accurate, this one. And then you probably notice that if I run it twice, then it's not really similar with the first one. Here, what do you think? What happened in here? Why I ran several times and it's not the same? What do you think? It's because I generate random variable. Yes, exactly. Good, Soren. So because I use randomness here when I introduce this one, meaning that yes, that's true. It's because of this randomness, then we have a little bit different estimate. But anyway, with regards to this randomness, we can see that the estimate quite close to the actual position. Okay. So this is you can see, and then you can try to experiment also using different initial condition. Let's say that this is 10. Let's say what happened is that the count filter quite converts quite fast. You see here that you see the evolution of this estimate. So the blue one, that is the actual, while the red one is the estimate. So in millisecond, it converts to the actual one. Okay, and then how if we have, let's say, 3 sensors? So this is a problem when one of master students working with me now is working with indoor positioning system. So let's say that you are operating a drones inside or indoor, and then you don't have GPS, of course, inside the building, but you could have like another sensor to estimate the position. Let's say the ultra wideband sensor. Okay, so let's say that you have 3 sets of sensor, and each set of sensor gives you X, Y, and Z. So this is somehow like indoor GPS. Let's say. So you have position measurement, position sensors, but for indoor, there are 3 sets of sensors that give you X, Y, and Z. Because of this noise, maybe this X, Y, and Z quite different. Okay, you can imagine that. But you could but you also have accelerometer. So in this example, what you want to do is that you want to fuse the data from 1 accelerometer and 3 position sensor. So this is the problem. Okay, you have 1 accelerometer and 3 position sensor. This position sensor give you a little bit different data. Let's say like the first sensors give you X1, Z1, X1, Y1, and Z1. The second one and the third one also give you different, like X2, Y2, and Z2, and then X3, Y3, and Z3. But you know that you only need 1 position, 1 correct position. And how to do that is that when you have more than 1 sensor that give you the same estimate, then you can play with this matrix A. This is the measurement matrix. So instead of having 1 and 0, you can have 1, 0, and then the second row is 1, 0, and the third row is 1, 0. So that is how to incorporate multiple sensor. Okay. Means that let's say that your error from this sensor will be also different. The first sensor has the error like this covariance 0.01, let's say. The second sensor has this error 0.04, and the third sensor has this covariance error 0.16. And then you can just run the count filter, and it will give you also accurate estimate.
I guess what about Q in this case? Won't we need to multiply that with some identity or anything?
Yeah, that's true actually. I don't know why, but why I didn't write it, but it should be times. It should be 2 times 2. Okay, I missed that one. But Q should be 2 times 2. That's true. Okay. Do you have any question? I hope you get an idea how to fuse IMU and GPS, or another positioning sensor positioning system. So it's basically we start with this kind of system that describe the motion, and then you build your state space, and then you can run your Kalman filter like this. Okay, it's quite straightforward. Adam, are you here, Adam?
Yes, I'm here.
Yes. So I think Adam will help you with the third example, aircraft pitch estimation. And then we will finish this lecture. But if you have any question, please, we can discuss this now. Do you think it's quite clear about this Kalman filter? So we didn't go into the detail of how to derive the equation, but what I'm trying to inform you in this lecture is that how it's work, and then what is the step on applying Kalman filter. Okay.
The only confusion for me was when you design the Q matrix, then you get, I would suppose you would get an estimate for one Y and not get multiple, but maybe that's just because I misread what you wrote in the Q matrix.
Okay, wait. What do you mean? Could you? So
you
this
have,
Q, yeah.
No, R matrix. Sorry. So you have three position sensors.
Oh, okay, yeah.
X, Y, and Z.
Yeah. So this one, this is only estimate. So let's say we think about drones moving in one direction. So this one is the position of the drones, not the sensor. So this equation describe the motion of the drones, and then you can imagine that these drones also has three positioning sensor, three set of positioning sensor located, let's say, in different places, and the sensor gives you X, Y, and Z. So what is changed is not the system itself, not this system, but the size of your measurement. This one, because this the sensors goes into this one. Was it clear?
Yeah, that part I understood. But but you changed the R matrix then, which is the noise to the. That's what I did.
Okay. This one, you mean?
Yeah.
Yeah, we need to change this because you see here that this H, the measure matrix, has if you look into this one, the size of this metric is 3 times 2.
Yes.
Right? So this is 3 times 2, meaning that this H times X plus this R should be also 3 times 3. It should be 3 times 3 because you have 3 sensors. Was it clear?
I think so. I'll just have to look into it.
Okay, that's fine. Yeah, Andreas, you have a question?
So there's the assignment,
Yeah.
the last exercise with the cruise control.
Yeah.
When we look into the web page with the link, there's a lot of information, and at the end they make a state space model.
Yes.
And I'm a little unsure about how much of this we need to incorporate in our program.
From the website, you only take the state space. So you don't need to go into the derivation. Just state that you have this state space, and then you want to apply or implement MPC.
Okay, so we just use the state space that they have made, and then we implement the controller for this state space.
Yeah, exactly. That's true. Not MPC. I mean the open loop.
Yeah, exactly. Okay.
Yeah.
Thanks.
Yeah. Any other question?
Last one.
Yeah.
You have taken 3 sensors. And for these 3 sensors, we have got 3 covariances. I mean,
yes.
for the value of R, which are the covariances, right? 0.01,
yes.
0.04. And we get this from the manufacturer's datasheet?
Yeah. Sometimes the manufacturer have this kind of information.
Oh. You have taken the value of Q and R to be 0.01. I mean, is there any scope for adjusting them or something, or you know?
Yeah, this is actually a good question. So this is really, really good. So in practice, okay, what happened in practice is that if you know this covariance matrix from the manufacturer, then you have to use it, and then you just input it into this matrix Q and R. But if you don't have any knowledge about this, you can try to measure. That is the first one. You can try to measure the standard deviation, or you can consider this Q and R as a tuning parameter for your Kalman filter. When you consider this as tuning parameter, basically you just put some numbers that, and then you look into the root mean square error between your estimate and the actual one.
Yes, because in the past we have modified them in the cost function to adjust and get the required waveforms. So okay.
Yeah. So it is actually good question and good issue about Kalman filter. So about this Q and R, you can measure it, but if you cannot, you consider this as tuning parameters. Okay.
All right, thanks.
Yeah. Because if you use bigger Q, for example, this is what happened. It's not really smooth, but still you can you able. But the actual one probably like quite smooth. But here is the estimate. So you can either consider Q and R as tuning parameters, or if you have knowledge about the covariance, then you just put it over in the equation. Very good. That's a good question.
Thank you.
Any other question? I hope it's clear. What do you think, Emil, Soren? Mikkel, what do you think?
Yeah, it seems clear.
Okay, that's good. So basically, it's Kalman filter is a bunch of procedure to estimate the actual state from some noisy measurement, and the formula is there. Then you can just run your algorithm. Before I close this lecture, actually I did a small research about this coronavirus. So as you know that this coronavirus transmit between people, and then the intensity of this coronavirus could be quantified, could be measured actually. And I don't know if you follow this news about this basic reproduction number. So basic reproduction number of the virus usually denoted by R0. If this value equal to 3, meaning that one infected person could infect 3 other person. So if the R0 equal to 5, so one infected person will spread this to 5 other person in average. If this R0 less than 1, then the disease will be maybe die out, so it will be disappear. But as long as this R naught greater than 1, then the disease will spread into the society. So I use Kalman filter actually to calculate the intensity of this coronavirus. I calculate for Denmark also, and it's what I get. It takes a lot of time, but this program also I put it here. So if you are interested with this kind of stuff, if you are following this coronavirus news, then maybe you are familiar with this basic reproduction number. It takes time, but let's see what we get. This one. So I use Kalman filter. So basically what happened in here is that this is quite typical, that at the beginning the virus will spread quite quickly into the society, because at this point, before this one, before let's say 10th of March, people are not aware that this virus entered the country. So the activity is still the same. But once we know that there are cases in Denmark, for example, so people take a precaution, some of them stay at home, so it will drastically lower the infection. So like this, and then this green line is where if this above this green line, then it will spread quite quickly to the society. But what we need to do is to keep this reproduction number below 1, because then we sure that the virus is under control and it will die out or disappear. And then the lockdown is, I think, 8th of March, maybe over here. But then we see that it starts to take the effect 3 weeks after the lockdown here. Of course, there is some delay because the incubation period of this virus takes also sometimes. You can see here that it's going down below 1. So meaning that now the virus is under control in Denmark, at least. Different story maybe if the country is open and then there is many tourists go to Denmark, and probably it will happen the same things. Hopefully not. Okay. But what I'm trying to say is that Kalman filter has a lot of application, not only in robotics or drones, but in other stuff.
So according to your research, you are already in a safe region, right?
Yeah, we are in the safe region, unless if there is some. Yeah, as I mentioned before, that if the country is open and then there is people from red zone area, let's say, where the outbreak still happen in Denmark, then it could have the second wave. So, yeah.
Could you clarify a bit on the confidence interval? What's that?
This confidence interval, because the calculation is really based on the infection time, and infection times is 9 days with standard deviation of 1. So it could be 8 days or 10 days. Therefore, I make this confidence interval, meaning that 90% of chance the reproduction number will be in this area. So we have a confidence with respect to the infection time, because we have some degree of uncertainty over there. Okay, that is only small research. But, otherwise, next week we will discuss about nonlinear filter which is an extension of Kalman filter to be extended or unscanted Kalman filter. But actually, we will focus on extended Kalman filter. Okay, do you have any question? Otherwise, see you next week, and Adam will handle from here. Good, Adam.
Yes, I'm here.
I will close this, and then you can call them back.
Sure.
Okay. See you.
Hi. Can you hear me?
Yes.
Yes. Yes. So basically, Agus showed you the example of a cruise control, which is this one, and you have the code on the e-learning, right? And if you go on that web page, so just try to open the web page and give me an ACK.
Can you repeat? So we should just open the web page.
Just open the web page and give me an acknowledge that you did.
Yes.
Yes.
You go there and you open the aircraft switch example. You have a dynamic system, which is the one in section 2 in the state space representation. So we have the state and the evolution of the state, and the idea now is to use the Kalman filter the same way as Agus used it in the cruise control example in MATLAB. So just try to implement it, and you can see how far you can reach. Does this sound good?
So just to clarify, so we have to implement the Kalman filter on this, and what is our measurement? Should we just read it through, or?
Yes, your measurement will be random noise, basically. So you just add the random noise in your covariance matrix.
Okay.
Adam, so we use the cruise control code to implement this one?
That's correct.
Thanks.
I mean, you can just start and implement it from scratch, but I think it's easiest to use the cruise control example and implement it from there.
Okay.
And as soon as you have any questions, or you don't know how to start, or I don't know what, just ask. By the way, do you have any questions about the assignment? Okay. Sure. So just one question that I received in 3.1. Okay, when we will reach 3.1 and 3.2. So in 3.1, you have to explicit the KKT conditions, and that's it. So just start with writing the Lagrangian, and then from that write the KKT conditions, as in the chapter 12. And then in 3.2, when you are verifying the sufficient condition, you will not met the criteria for applying the theorem, which means that you have just to look at the problem. And you'll see that it's rather easy to see the minimum. So no need to formalize it with Hessian.
Hi, Adam. For the aircraft pitch modeling, they have already provided us with the state space equations. So should we use those?
Yes, definitely. So basically you are using the A, right?
Yep.
And you are applying it in your Kalman filter representation, which means that covariance matrix F.
Okay. Thanks.
Sure. And the same thing happens with G. So basically your G will be the B, and you multiply it by the timestamp. Right? Yeah.
So Adam, so you mean we have to piecewise multiply f like this? Or what do you mean we have to multiply the matrix with the timestamp?
You mean the covariance matrix? Right?
I heard you just said the system matrix, but maybe I just misheard what you said.
Yeah, no, I was speaking about the G.
Ah, okay.
So basically in the Kalman filter formula you have the F, the G, and the noise. So the G is your control, so it is your B matrix.
Yes.
And you multiply it just by time step.
You mean like this?
Right? Yeah.
Okay. So why do we do that?
If you look there, it basically asks you the control for time step, right?
Yeah.
So you discretize it, just.
Okay.
And then you add noise. So you basically just suppose that you have a distributed control, and then for each control you add just noise.
Okay.
It's just a quick question. Do you remember the numerical optimization formula that you were using to verify the unconstrained optimization in assignment 1 in MATLAB?
Can you repeat?
Do you remember the MATLAB function that you were using for unconstrained optimization for the numerical solution?
Roughly, yes.
Can you please just tell me it? Because I don't use MATLAB.
Oh, so you need the MATLAB version or not the MATLAB version?
The MATLAB version.
Oh, I did the first assignment in hand.
I mean just the formula. Function, I mean. Sorry. Because then the assignment asks for a sketch the numerical solution by the script.
Okay.
Oh, like the Newton method.
Mm-hmm. If you remember just the name of the script that you use in MATLAB.
Okay, I'll find it.
We used the one that August gave us in the class. He put up one a class assignment we could do.
Okay, thanks. No, I couldn't find it. Thanks. Oh, sure, sorry. You don't like my mechanical keyboard?
No, not very much.
Adam, how can we validate if we have made it correct?
So we can just check together.
Okay.
If you share the screen.
Sorry?
If you share the screen.
Okay, I've shared it now.
Okay. So let me check. Okay. Yeah, if you do like this with the F covariance matrix,
yeah,
you will get always very small values. So then you multiply it by your state, right, in the Kalman filter equation.
Yeah.
And you will not get the proper system. So what I would do is to add the identity matrix.
Okay.
Exactly. Then let me check G. Yeah. Okay. I'm not sure on the X and X hat, but might work. Try to run it.
Okay.
So, no, not really.
Maybe that should be minus there.
Give me a sec.
I
don't agree with that.
Okay, so plus?
Yeah.
Okay.
I will do plus, okay. But then you don't need the identity matrix there.
No.
Just now, sorry. Yeah?
Yeah, okay, so like this.
Okay. I guess there is something that is wrong with your initial guess. Close this.
Yeah.
Initial guess. Yeah. So basically here you care about the last one, right?
Okay. Yeah.
So put 1 there instead of 0.
Okay.
And the same for X hat.
Okay.
Okay. I'm not sure about the control. It looks kind of high, but try. That work? No, not really. I guess the control is too high.
Okay. So like 10 or?
That might be better, yeah. Still nothing. Let me check the for loop. No. Especially I don't get it why it goes back. So it's estimating for a while. Try 1 as control.
Okay.
But I was still checking the for loop. I think there is something wrong there. So just go back to the for loop, please.
Yeah.
I think it shouldn't be xmin in the X hat, but I guess it should be the previous X hat. Let me check what I've done. Yeah. And that's correct, because then you estimate that. Yeah. So the last line, when you're updating the x hat.
Yeah.
Right. I would use x hat multiplied by your age matrix instead of x min.
Okay.
Let me check all this stuff. That makes sense. Makes sense, yeah. Okay. Still not there.
Okay.
Interesting.
Megal have written something in the chat. Maybe he got it.
No, it's wrong. That one.
Okay.
Let me check the state.
State?
Yeah, stay there. Don't move. Yeah, sure. Yeah. So basically, you are multiplying, but you are multiplying it with the identity matrix inside. So it's relatively low, because you are then discretizing it, but you are discretizing it with the identity matrix inside. So what I would do is to erase those 1, plus, minus 1, and the identities on the yeah, exactly, as well, and yep, and make plus, bright plus, yeah, identity thing. Okay, almost.
Shouldn't be minus there, or I'll just try it.
Oh yeah, you have to write. Okay. Let's check the interval.
Interval.
Yeah, stay there. Up, 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 up. Okay. More up. Yes. Yeah, that one is too big. I would go from 0 to 1. So TF is 1. And yeah, times that is okay. Yeah, I guess. Okay. Try now. No, but still it was plotting something that it shouldn't. Almost. What is that? Okay. What you're plotting?
What I'm plotting it's just the x's, like the state.
But wait. Where is Skype? Yeah, here. Yeah. So basically, the output, if you look in the model, it's just the third column.
Okay. Yeah.
I guess that one is an. Yeah. Yeah, that looks correct.
Okay.
Give me a second so I can check mine. That looks almost correct.
Okay.
Wait. So mine looks like this. How can I share the screen? Do you have any idea how to share the screen?
Yeah, down in the bottom right corner, there's two small squares besides the chat icon.
I don't have it.
I'll send an image.
Yeah, right beside the heart, to the left of the heart.
So I have like 3 points there.
If you click the 3 points, it should come up with an option including share screen and stuff.
I don't have it. Send me an image. I'll wait. Send me an image of that.
It's like a note button right next to the end call on the right side.
I still don't have it. Just give me a sec. I will send the screenshot. So this is the solution. And this is my scatter. No idea. And if you share the screen again, we can check what is wrong.
Yeah, okay. So should I run it for 10?
No, go for 1.
Okay. Let's see.
Oh yeah, of course. So the Q.
Yeah.
You have a 3x3 A matrix here. So just multiply by. Where you're using it?
So down here. Square root.
And then you have random by dt, right? But you have here 3x3 matrix. So you need a 1x3 vector.
Yeah.
Why not 3x1? Maybe I just have to look at the screen.
Yeah, you are right. 3x1.
Oh, okay.
Yeah. You see? No. This is an issue. Try to change the arm matrix.
Okay.
0.05. Still not much. Can you just send me the code, please?
Yeah. I'll do that.
That's the easiest.
So, I think it's this one.
Okay, thanks.
Adam, just a quick question.
Sure.
Is K supposed to be a matrix or a vector?
Which one, sorry?
K, the gain?
Where is K? Give me a sec.
It's on 46, right there. Because I get P mean to be a 3 times 3, 8 is 1 times 3, and sigma is a 3 times 3. And I can't get it to add up.
I guess that one should be a vector. Yeah. Because we are multiplying P, H, which is a vector, and then we are multiplying it by sigma, right?
Yeah.
Yeah, that should be a vector.
Okay, so how come sigma becomes a matrix? And we have P, which is a covariance matrix, and then we have sigma as a matrix, then it doesn't...
Okay, sigma is a matrix.
Because I guess sigma have to be a matrix, because otherwise you can't take the inverse of it. And it makes sense that the P mean is a matrix because that's a covariance matrix.
But yeah, that's correct. So you, yeah, so sigma is 3 by 3, right?
Yeah.
mean is just a value, and then you have H transpose, which is 1 by 3. So then in the end you will have 1 by 3.
1 by 3. Maybe I have the wrong dimension of my H then. Yeah, that's right. Okay, thank you.
You're welcome. So I'm looking at your code, just give me a sec. Okay.
I still can't get the K to add up, so if you have a second at some point, then I would need some help.
Just one sec. Okay, go ahead with the K.
Okay, so for some reason I have the same dimension of the H as you, so it's 1 by 3. And I get sigma to be a 3 by 3.
3 by 3.
And then I can't seem to get that P min times H dot times sigma to work. I don't know why.
Interesting. Give me a sec. I have sigma that is just 1 by 1.
Sigma 1 by... But how do you get that when sigma is the inverse of H times P min times H, which is a scalar, but R it's... Oh, maybe it's because I have R as a matrix. So why is the covariance of... Oh, that's because we're only measuring one position, I guess.
I got lost.
Okay, so it's because I had R as a matrix and not R as a scalar.
So, no, wait. So you have R Yeah, okay, yes, exactly.
Yes. Okay.
So then you will have the H, which is 1 by 3, H transpose, which is 3 by 1, E mean, which is the matrix, right?
Yes.
And then, yeah.
Yeah, and then it adds up.
That's 1 by 1.
And then we have K is a vector, right? It's a 3 times 1 vector.
Which one, sorry?
K is a 3 times 1 vector, right?
Exactly. Yeah. I hope I got it.
So what do you set the input value to, and what do you set the initial data to?
Which one?
The input U and the initial data. What do you set that to?
So I started the control with 1.
And then the rest with zeros.
Yeah.
Which value do you have for dt?
So my dt is 0.001. 10 minus 3.
Okay.
And what's your TF?
1. But I mean, if you put 10, it's just stretched over time, so it shouldn't change that much. Then you have just to zoom on the right area.
Okay, because I get a weird result. I just have to figure out where it goes wrong.
Can I see it? I was actually trying to fix the code that you sent me. I ended up by doing something with my no code, and now it does not work.
Okay.
No idea what I have done wrong. Lol. Yes.
Try to set your initial points to 0, 0, 1, both on x and x hat.
Yes.
What are you plotting?
I'm just plotting whatever I was plotting, and that is the x array and the x hat array.
Try to plot that from 3 to, so only the column 3.
Oh, that makes sense, maybe. So here.
Yeah.
Yeah.
Oh.
Yours is still fucked.
Yes.
So can I see your F and G? You have to multiply that with dt.
I thought it was only G we had to multiply like that.
I think it's both.
And I multiplied G down here. Oh.
Ah.
I think, okay, let's do it this way. Then we keep track of what we're doing.
Yeah, you also need to add I to your F.
Yeah, because to your F.
Like an identity matrix.
It gets like a really small number. I like in I hurt my eye.
Why should I add that?
That's I can write it in the 2 seconds.
Then I added a dt here, but that's to the random. Is that correct?
I haven't got that.
Didn't get that. That's what I was wrote.
Oh yeah. Sorry, to the random.
Yeah.
Yeah.
Okay, let me try again.
But you have that's dt in front. Yeah, sure.
Okay, now we can see the true value. Ah, they are overlapping. That's nice. Why is it making solid? Okay, I get the correct answer now, I think. I get some answer now.
I agree. The one that I sent before was wrong. That one is correct.
Okay, nice.
So also yours, the exercise that you sent me is correct.
Okay. Emil, do we get the same here?
Yeah, almost.
Almost.
Except mine.
So shouldn't it be stable, the value we're getting, because it's a pitch value? Shouldn't it flatten out instead of increasing all the time?
So if you try to put 10 in TF instead, just guessing.
Oh, I put time here and here.
Yeah, but if you change TF to 10.
What then?
You can see that it's kind of stabilizing.
Kind of.
We do not really get the same weather.
Oh. It doesn't really change much, Emil. If I now spend it to 30.
Yeah, okay.
Let me check. But I guess that one has a steady ascent, so it might make sense. Let me read it again.
But it doesn't say anything. It says like we assume the aircraft is in steady cruise at constant altitude and velocity. This the thrust, drag, weight, and lift force balance each other out.
Yeah,
we will also change the. Assume that the change in pitch. Okay, so I would assume that it would go to constant.
You said like this, it makes sense. Just give me a second.
Oh, but our input is elevation deflection, but I don't know what that means.
Maybe the plane is just looping around. Okay. So the elevation deflection is a flap that is wrapped up, so it would change its direction. So it makes sense that it's not constant, like it would ramp or go smooth when we.
Let me check. Yeah, I guess so. If you try to plot it over 10, then you see that it stabilizes, it goes up, stabilizes, goes up.
What do you mean? Can you show your plot?
Sure. Wait. Because for some reason the Skype version on Debian doesn't have the shared screen button. I have no idea why.
Yeah, that's how it is sometimes.
Or maybe just me. I mean,
it might be because you have your webcam turned on. Sometimes they don't want to share both.
Okay.
Eating up the broadband.
Not really. No? Oh, never mind. I send the image. This one. Wait, this one. So this is over 100.
Okay, yeah, so it seems still keep rising.
Yep, but if you look, it goes down, then it goes up, and it's mostly the same behavior over time. So it's actually something that I would expect.
Okay, so why would you expect that?
I think they are modeling just the ascent in this case. So you're supposing that it's ascending and then they are using a different system.
Okay, but right now we are only modeling the dynamic and then we're putting some error in.
Yeah, that's correct.
So I don't see the connection.
No, but basically you will have different dynamic system for different phases of your flight.
Oh, yeah. But yeah, okay. So that's maybe because the value we are changing, the input value, that's
That's the flap that changed the steering direction.
That's correct.
Yeah, okay. Okay. So I guess we get the same result then, because I get pretty much the same.
Yeah, that's correct.
What else are we supposed to do?
That's it. Yeah, if I zoom is exactly the same as yours, so.
Okay, that's good.
Okay, how are the others doing?
I have the same.
Yeah, same here.
Yeah, same.
If we have the same, are we then finished? Or
Yeah, that's correct.
okay. Is there anything else for today? Or
No, that's it. If you have any question, we can discuss them, but if not.
okay.
Okay, bye then.
Bye.
Yep, thanks. Bye.
Thanks.
Bye.